With all of this in mind, we come to the crux of our presentation today, the in situ confined synthesis of copper encapsulated silicalate 1 zeolite. As it stands, the capture of iodine with solid absorbance has been demonstrated to be a feasible method for commercial application compared to wet scrubbing of iodine-containing off-gas streams using other alkaline solutions. A variety of porous absorbents, including activated carbon, aerogels, covalent organic frameworks, metal organic frameworks, and zeolites as well, with intrinsic properties of their porous structure, high specific surface area, and uniformly dispersed functional groups, showed exceptional advantages in capturing radioactive iodine. For example, silver-exchanged zeolites, such as silver-loaded faujasite and mortonite, have been considered as benchmark sorbents for iodine capture for the removal of I2 and organic iodine from spent fuel reprocessing plant off-gas streams. However, the toxicity and high cost of silver reduce its attractiveness for industrial applications. Furthermore, all silica zeolites exhibit stronger hydrophobicity and acid resistance than other aluminosilicate zeolites, and can be used as an ideal carrier material for the separation of radioactive iodine from gaseous radioactive streams containing water and acid gases. However, there are still some drawbacks with microporous zeolite confined absorbents, as the pore size of conventional zeolite is typically below 2 nanometers and it limits the diffusion of gas molecules and the accessibility of metal active sites. Until now, zeolite confined metal nanoparticles, or NPs, for removing gaseous iodine are still quite scarce. The design of high stable zeolite confined metal absorbents for effective iodine capture from gaseous radioactive streams remains highly desirable. As such, the all-silica zeolite silicalate 1 encapsulated copper metal nanoparticle, or copper at FSO1 for short, was synthesized through an in situ confined synthesis strategy aiming to enhance radioactive iodine capture. Typically, copper 2 nitrate trihydrate was dissolved in deionized water under stirring. Tetraethyl orthosilicate and tetrapropyl ammonium hydroxide solution were sequentially added, and the mixture was stirred at 90 degrees Celsius for about 24 hours pre-crystallization. An aqueous solution containing ammonium fluoride was then added to the mixture and kept vigorously stirring for another 24 hours. The obtained gel was transferred into the Teflon-lined stainless steel autoclave and reacted at 120 degrees Celsius for more than 72 hours. After cooling to room temperature naturally, the light blue solid product was filtrated, washed with deionized water, and dried under vacuum at 70 degrees Celsius for another 24 hours. In the end, copper at FSO1 was obtained after calcined at 550 degrees Celsius for only just 5 more hours under a hydrogen-argon atmosphere, as shown in the pathway here.